ON15, paper 43, question 11 is a great question to test your understanding of absorption and attenuation. Let's start off with this one. An X-ray source placed on one side of the material the metal as shown. Here got source, X-ray, pew, 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 come over. Now we would think that the X-ray beam would just go like that. Okay, but hang on a second. Intensity of X-ray is measured at points A and B. So you have some intensity here. Let's call this I0. And after that, you pass through another intensity. State two reasons other than absorption. Of course, you pass through metal plate, you will get absorbed. This will absorb some energy. So the intensity will decrease. But other than that reason, you need two other reasons why the intensity here and here is different. Why? Means I thought intensity just go through, absorb, that's it lah. Wait. We learned so many things. We learned that, okay, there are, let's draw many X-rays. So X-rays can come through, but hang on a second, this is a source. Maybe the X-ray spread out leh. Wow, that's another problem leh. If spread out, then your intensity will be different because the area is changing. This beam is not very well collimated. Not very collimated. Another problem is maybe some X-ray come here and then bounce back eh. Wow, reflection bounce here, bounce there. Maybe it go inside the metal and then it do some funny diffraction thing and then start to spread out. What is this? Maybe it go here and then diffract this way. So all kinds of funny thing can happen in real life. It's not as nice as parallel ray come in, parallel ray pass through. No, this is how it will look like, maybe. So we're going to talk about some of those reasons down here. What a mess. What a mess. So what are the two reasons? Let's start off with the first one. You can talk about the beam itself. You see, where is your aperture? No aperture. Your beam can just spread out as big as it want to. So your beam's not very parallel. So that could be a problem in this case, in this particular setup, why the intensity is different. So your beam is not parallel as it should be. Not as parallel as it should be. So there's some kind of increase in area lah. So here you can say increase in beam area as you travel from A to B. This one not in the mark scheme, just give you an extra heads up. And don't forget, intensity is power per unit area. Area changing, your intensity also changing lor. Changing because the beam is spreading out, not because it's getting absorbed by this metal plate. Because it's spreading out. Oh, that's not good. The other thing we can talk about is all this mess that can happen when X-rays hit the metal. Reflect, diffract. What else we want to talk about? Let's write them all here. So the main idea is you can say there's some kind of scattering. Okay, when it hit the metal, hit electron, hit atom, there's some kind of scattering that can happen. All the rays go in different directions. You could also talk about the idea of reflection. So reflection from the metal. Once it hit the metal, it bounces back out. It happens once in a while, okay? And lastly, you can talk about diffraction. Inside the metal, it's kind of like scattering also, a little bit related but not entirely the same. So you can talk about diffraction in the metal lattice because there's a whole bunch of atoms inside, right? Sometimes it will diffract and spread out because it's a wave. Sometimes it scatter, bounce here, bounce there, bounce here, bounce there. Because photons are waves, but also particles. So all these effects can apply to them. Collide, scatter, collide, reflect, diffract, reflect, all these things. Any two of these points, you mentioned any two of them, that's B2. So here we have 1, here we have 3 possible reasons why the intensity might not be the same. Because not all the rays made it through, because beam's not parallel. I mean, even if they made it through, they're spreading out. All these problems in real life. That's why we talk about all these things of how to make sure you get the best image possible. Anyway, let's look at an actual scan. A specimen of muscle and bone. Why the bone suddenly end here? I don't know what kind of part of your body have a bone that suddenly ends abruptly. Anyway, parallel beams of rays are incident on the specimen. This is very good. Parallel. This is what we want, so we can use our equation later. Specimen total thickness, one section got bone, one section don't have bone. So the data for the linear absorption attenuation coefficient for bone and muscle is shown. Wow, bone so high means it absorbs a lot of the X-ray energy. Muscle, very little. So muscle, X-ray no problem can pass through. So before we go to the next part, think about this first. When the X-rays come through, let's say here, I'm going to call this I2, and the X-ray come through here, I1. Which intensity you think will be bigger when it pass through? Okay lah. In the beginning, they all have the same intensity, I0. One goes through bone and muscle, one goes through muscle only. Which one you think you have higher intensity? The answer is, this one will have a higher intensity compared to I1, which have lower intensity because of the bone. The bone will cause the X-ray to lose a lot of its energy, so the intensity will drop very quickly once you go through bone. So now we're going to actually do the calculation to compare these two rays, I1, I2. One go through muscle, one go through bone and muscle. Let's go to the next part. Okay, calculate the ratio. Intensity of X-ray incident over intensity of X-ray emerging. So incident and emerging. So I guess we have to redraw some pictures, right? But firstly, you remember the equation for intensity? You don't remember equation, anything also cannot calculate leh. So intensity I equals to original times this factor to account for the loss of intensity. The exponential decrease. It's half and half and half and half each time you go a certain fixed distance. So now we can draw out the diagram again here on the left side. And this pink color here is the muscle. So X-ray initially come in. This is what we call I0. Then when it's inside the muscle, there's something happening, right? The X-ray will, we look at it earlier, X-ray will decrease in intensity as you travel a certain distance, which is here. So in total, I mean, you want to compare incident with emerging. Incident is I0. Emerging is what comes out at the end. Here. I'm just going to call this I. Okay. And the distance that the X-ray has traveled inside this muscle, this pink color muscle, is the total distance of how much? Check the answer. Check the question. 4 cm. So right here, 4 cm. So travel 4 cm in muscle, come out. What's the ratio? Let's do our ratios. So you can talk about incident. This one is I0. So we're going to write here I0. Divide by, down there is what? Emerging. What comes out at the end? Oh, this one is the one we calculate. I0 equals to I0. I equals to I0 E negative mu X. So you just write here, I0 E negative mu X. Here you can do a bit of adjusting. You look carefully, I0 and I0, those two can cancel out. So you're left with 1 over E negative mu X. And if you don't like negative, you can simplify this a little bit more. The negative sign just means you can rewrite this whole thing as E mu X. Looks pretty nice. What mu do we use? Well, this muscle got some mu, right? Attenuation coefficient. You can check the front part. What is it? Mu for muscle, 0.227 cm negative 1. So let's write that down. 0.27 cm negative 1. There we go. So we can plug in our equation either into this one or into this one, whichever one you want. I'm lazy, so I'm going to use the shortcut. I'm going to use this one. E mu. What's mu? Mu. 0.27 cm. And the distance you travel, 4 cm. 0.27 cm negative 1, sorry. So you see, your cm and cm here must be the same unit. If centi, you centi. If millimeter, then you millimeter. But nice thing is, they'll cancel out when you multiply them together. Cm negative 1 times cm. So you press calculator. You should get a value of about 2.945. This is a ratio. So you can keep it in decimal form, no fractions. Final answer, I can choose 2 or 3 SF. I'm going to do 2 SF. So 2.9. So this one is an A1 mark. The other one is if you knew how to, do a substitute or anything inside here. This one I'll just put here, C1. Sub into the E mu X. And that's your first one. This one, not too bad. You just plug in and okay liao. Let's look at the second part. Also calculating ratio. But now for the part, for the beam that passed through the bone and muscle. Wow. So what is the bone and muscle? Okay, baby, faster go back and see. Okay. So just now we calculated this. Beam pass through muscle. What's the intensity ratio of the emergent beam to the incident beam? Now we look at this part. Oh, yo, muscle, bone, muscle. How to calculate? Okay, we redraw the thing. We stay calm. We take a deep breath. And we redraw our diagram on the left side. Now, here's our muscle, bone, muscle. Pink, gray, and pink. So I'm going to once again label the mu for each of them so that we can see this, which is 3.0 and 0.27. One for bone, one for muscle. Underline lah. Bone got this mu. Muscle got this mu. Okay, let's look very carefully. If you want to ratio, what are we ratioing? We want to ratio incident beam. Let's put this one here, black color. Incident beam got I naught. At the end of the day, come out, got some I. These are the two we want to ratio, but what happened in between? Got so many leh. How to think about this? Okay. We stay calm and we think about the first part. Think about this I naught go through muscle. How far does it travel before it hit the bone? You do some subtraction and see. Okay, we go back to this diagram. What is the distance here? There's two parts here. No. But I do know the total muscle part could be 4 minus 1.5. So that's about 2.5 cm for both of these muscle. So it will pass through a total of 2.5 cm of muscle. So I can kind of rearrange this thing, you know. I say, I don't know each muscle layer is how thick, but I know in total, the muscle will be 2.5. So I'm going to cheat and I'm going to, because I can, I'm going to rearrange the muscle. There we go. So we now have a big fat 2.5 cm. 2.5 cm? I think I wrote 2.5. Yeah, 2.5 cm of muscle. Then you have the bone. How much of bone is there? According to the diagram, we have about 1.5 cm of bone to go through. Now there's two parts. So think of the muscle first. When your ray comes through the muscle, when it comes out on the other side, what is the intensity here? This intensity, we can say is I equals to I naught E mu of muscle, that's why it's pink color, times the distance it traveled, which is the pink color X. Then this ray is what will go into the bone. Wow. So the bone, we have another equation, I equals to I naught E mu X. But what is the I naught? I naught is going to be this thing inside here. Because what come out of the muscle will now go into the bone. Wow. Okay lah. So remember, this part, pink color, is this. After you go through muscle, you have this attenuation and all this happening. Now you send that thing into the bone. After it come out from the bone, this, wrong color. This wave, this one here, is going to be I equals to I naught E mu X. But what is the I naught? Let's label this here. This will be your I naught that goes into the bone. Pause the video and digest that a bit if you're like, what is happening? Nani? Okay, so if we sub in the equation of this final intensity that comes out of the bone and comes out of the whole thing, you can rewrite it as this one equals to, now what is this I naught? Whatever came out of the so-called I naught for the bone is what came out from the muscle. So that would be I naught of the original E mu X that went through the muscle times what went through the bone. So you see the coloring is a bit different here. So this is like the so-called I naught that went into the bone lah. Okay, so this big black I is the final intensity that comes out through the bone, the muscle, everything come out. That's the final one. Okay, you can draw the diagram separate lah. Muscle, bone, you separate a bit, give some space, then you can see how it's different. So now we can ratio. Oh, finally. Okay, so the ratio is, what was the ratio again? Incident over emerging. Incident is what goes in, emerging is what comes out. So now it's a little bit more complicated. What goes in is just I naught. So we're going to label that. This is incident. What emerges at the end is this one. So we can write the whole thing down. Oh my. How am I going to write this without color coding? Okay, I'm going to follow the color coding. So I naught E mu X, for all this mu is for bone, X is for bone, times the one for grey color, which is just mu X for bone. Alrighty, let's do the math over here. Now we can say, oh, I naught is the same. Now this I naught of the pink color is the same as the one up here. So we're just going to put it as that. So we can cancel out I naught. What is left here? I forgot the negative. Negative mu. Here also negative mu, negative mu, negative mu everywhere. Okay, there we go. That looks more correct. I was like, something's not quite right. So I'm going to shortcut and move all this up because I don't want the 1 over E. So this will just be mu X of the muscle times, okay, right here, this is all of the muscle, times E mu X of the bone. Wow, this is interesting. Can multiply like that one, miss me? Yeah, lor. So for every layer you pass through, the ratio you just multiply together. So make sure you know why it is so lah. So let's calculate all the things inside here. For E, what's the mu of muscle? 0.27. Okay, so right there 0.27, all in cm, right? Okay, all good. So times 2.5 cm in total. Total muscle that you pass through is 2.5. Then you have the bone times E to the, what's the mu of bone? Mu 3. 3.0 times. How much of bone do you pass through? 1.5. So you write there 1.5. All this in cm, so we're all good. Now the final answer is a huge ratio. You will get a value of 176.796666. I'll just put here. So on and so forth. I'm just going to round it off to a number of 180. 2SF. Whew, this is 2 marks. So this is A1. And if you sub in, well, you kind of do this calculation, C1. Okay, you can do the negative version lah. 1 over e to the power of negative. Okay, like what we did up here. You can either write it in this form with the e to the power of negative, or you just get rid of the negative and 1 over the whole thing. Become like that. Also can. So this one's pretty tricky. Okay, so just remember, you can split up into section. What comes out of the muscle goes into the bone. And you have attenuation again. So that's why there are two E terms inside here. Because you are going through muscle and also bone. Okay, so make sure you can wrestle with that until it makes sense to you. Now the last part, using your answers that you talked about previously, suggest and explain whether this image have a good contrast or not. Wow, what is contrast? We learned about it in the theory video. Think very carefully. How do we know based on this answer? They say use your answers, ma. How do we know based on this answer whether we have a good contrast or not? Let's think carefully of what these actually mean. So the ratio of 2.9 is the ratio of incident over emerging. That means what this really means is I naught is roughly 3 times larger than what comes out. That's what it means. And the other one is saying that your I naught, what goes into the muscle bone combo, is roughly 180 times larger than what comes out at the end. So if you compare the picture together, this one, where is it? We said this one is lower, this one is higher. It's going to be a very, very big difference, you know, because this one is going to be much lower intensity. And the other one is going to be much larger intensity when it comes through. Compare lah, relative. Very, very big difference. So this one, very low intensity. So the color will be quite white. Very white. Very white. In comparison, the other one, a lot of X-ray come through, so it'll be much darker. So is this a good contrast? I think it's a pretty good contrast because if you compare the ratios, that's very big. So that's how we're going to write the answer. Very good contrast. How to explain? Okay. So we're going to use the answers above. So what we can say now is that talking about the ratio, since they asked us to use our answers, so you can say that since the ratio is a measure of transmission, okay, ratio is how much comes through, that's what we call transmission. We are transmitting across a medium. Then we compare two values. One ratio 2.9. One ratio is 180. Oh my goodness. So you can say 2.9 and 180, which are the ratios, are very, very different. So the intensity reaching the film after going through all the bone and muscle will be very different at different areas. One got bone, one don't have bone. So here you can say, hence, I will call it good contrast. I'm pretty satisfied. If the ratios are almost the same, then you're like, almost the same also, the same color, so you cannot really tell if there's contrast or not. So this one is B1 and B1. Last thing to add on is, I'm gonna redraw this thing. Okay, muscle, and bone here. Let's make the bone a bit longer. So what is contrast in this context? So you see, if I have two rays, this one come through here and this one come through here, both of these have incident and then emergent intensity. And the ratio is the same. For the first beam, it is going to be about 3 times. Second one is about 3. So this will be the same color whenever they reach the film. So same color means no contrast. No. There's not much difference in the color. These two. But if you have another beam, let's use a slightly different color. Let's use purple. No, let's use blue. Dark purple, sorry. Then this one, come through muscle, come through bone, and then finally muscle. Ooh. This one, the ratio of its incident to emergent is 180 times. So if you compare this 180 with this 3, oh, very big difference. Very, very big difference. So you have difference when comparing these two. Very different intensity and very different color. After all, the intensity they come in the beginning is all the same. This one, all I not, all the same. But come out all different intensity. So you want them to have very different intensity and you can tell with the ratio. So that's all for this video. Good test of understanding of how to use the equation. The rest is pretty much all ratio everywhere already lah. So go and check out the other examples, the other one that will be posted. And we'll move on to the last part, which is CT scan. X-rays, but moving in a circle. That's the final part for a chapter on quantum mechanics, quantum physics. That's all for this video. I will see you in the next one.